So let's have a look at these logical operators in a bit more detail then. So the first one we're going to consider is the AND operator, okay, or the AND logical connective. And we use the AND logical connective when we want to assert that two statements are both true. So let's have a look at an example again. So we're going to assert that the value of pi is between the real number 3 and the real number 4. So in symbols we would write 3 less than pi less than 4. Now that statement using those symbols, 3 less than pi less than 4, can actually be split into two base statements. So what that really means is that pi is greater than 3 and pi is less than 4. So in this case we can see that given that one initial statement, we can actually split it into its comprising parts, which would be made up of two statements brought together using this word AND, this operator that we're going to use. So this is called the conjunction of the two statements, pi is greater than 3, and the second part of the conjunction would be the statement pi is less than 4. We're bringing those two component parts together using the logical AND connective. In terms of the symbols we use, the symbol for AND would be an upside down V. Okay, so if we see this upside down V, we read it as the AND logical connective. So let's just take a definition again. So we're given formal propositions P and Q. So that just means that we can assign a truth value to P and a truth value to Q. And P and Q both represent statements, propositions that we're actually using. The compound statement then, P and Q, is a formal proposition itself. So P and Q can also be assigned a truth value of either true or false. And this is known as the conjunction, and we read it as P and Q. So one of the methods we have to actually explore the result of forming these compound statements using logical connectives is through the use of the truth table. So truth tables will really demonstrate for us the result of combining two base propositions together using a logical operation. So if we're given any two propositions, P and Q, well, each of them has two possible truth values. So P can either be true or false, and equally Q can either be true or false. So if we think about the number of permutations that we can actually form, taking into consideration that P and Q can have either of those truth values, there's going to be a total number of 4 possible permutations of truth values for P and Q. So to actually list those out, we would have P is true and Q is true, P is true and Q is false, P is false and Q is true, or P is false and Q is false. So those 4 possible combinations are going to exhaust all the possibilities that we can actually take in considering P and Q and the various values that can be assigned to them. So for each of those combinations, we can look at the effect of using the AND operator to form the compound statement P and Q. And to do that, a truth table is a very useful way to actually represent and display the result of the combinations. Okay, so let's have a look at the actual truth table then associated with the logical operator AND. So we can see in the table on the very first row we've got P, Q, and the final column is going to represent the result of combining P and Q together using the AND operator. And then each of the subsequent rows are actually specifying the combinations that can be constructed for P and Q using the different truth values. So the first row in the table, we're actually specifying the truth values. We can read this as P takes on the truth value of true, Q takes on the truth value of true. The result of combining P and Q together using the AND operator would then also be a true statement. Okay, so if P is true and Q is true, then the compound statement P and Q is also true. The second combination we have then is that P takes on the truth value of true, Q takes on the truth value of false, and then we determine the actual truth value of the compound statement P and Q. So in this case we have P is true, Q is false. The compound statement P and Q would then be false also. The third line, the third combination we're considering, is when P is false, Q is true. In that case, P and Q results in false also. So the truth value assigned to the compound statement P and Q in that case is false. And the final row we have P is false, Q is false. The compound statement then, formed using the AND logical operator, P and Q, would also be false. So this is the truth table for conjunction. So conjunction, we just think of the AND operator. And the truth table as displayed here is the full table. There are no other possibilities available for us in terms of the combinations that can be formed with P and Q. Okay, the next logical operator we're going to consider is the OR logical operator. Okay, so anytime I use the word operator in terms of these logical operators, we can also think of them as a logical connective. It's just corresponding terms that mean the same thing. So we use the OR logical connective when we want to assert either of the two statements are true or both statements are true. Okay, so this is called the inclusive use of OR. So let's consider the following statement: A equals 0 or B equals 0. Well, this statement is true as A is equal to 0, regardless of the value of B. And it's also true if B equals 0, regardless of the value of A. Okay, so because we're using the logical operator OR, in order for a compound statement to be true in this case, we only need any one of the base component parts to be true. So the statement is also true if both A equals 0 and B equals 0 are true. And this is called the disjunction of the two statements. The two statements, the two base statements we're using in this case, the first one is A equals 0, the second one is B equals 0. And we're going to combine those two base statements together using the OR logical connective to form a new compound statement. And that's going to be called the disjunction of the two base statements. Okay, in a similar fashion to how we looked at the truth table for AND, we can also consider a truth table for OR. So we'll come to that in a moment. In terms of the symbol we use for the OR logical connective, it's a V-type symbol. Okay, so and the definition for the OR logical connective, or for a disjunction, given formal propositions P and Q, the compound statement P or Q is again a formal proposition, so we can assign a truth value to it, known as the disjunction, and it's read as P or Q. Okay, let's go through the truth table for this OR logical operator. Okay, so in the same way we have four combinations of truth values for P and Q, the same will hold true when we're actually constructing the OR truth table. So what we see here is the first two columns in the table are going to be identical to that for the AND truth table, because the combinations remain the same. The final column, though, where we're actually specifying what P or Q is, will be different. So let's just go through the truth table row by row and see what the result is going to be. So let's take the value for P to be true, the value for Q to be true. Well, then the resultant compound statement P or Q will also be true. The second combination here, let's take P to be true, Q to be false. Well, then the compound statement P or Q will also be true in this case. The third combination, P is false, Q is true, P or Q is going to be true in this case. And finally we have P is false, Q is false. In that case, P or Q will be false also. So this is the truth table for the OR logical operator, or the truth table for disjunction. And we can think of it in terms of an example as well. So if 1 equals 1 is the proposition associated with the propositional variable p, and if q is another proposition, say 1 equals 2, well, we know that 1 equals 1 is true, we know that 1 equals 2 is false, so it would be represented by the second combination in the truth table. So in that case, p is true, q is false. If we form the compound statement p or q, well then what we're saying is 1 equals 1 or 1 equals 2. And because at least one of those propositions in the disjunction is true, the final compound statement will also be true in that case. The last main logical operator we're going to consider is the not operator. Okay, so this is essentially an operator we use to negate the truth value of any proposition. So if we're given a proposition that is true, the not operator acting on that proposition will result in a false proposition. So let's take an example of that. Let's consider the statement a is not equal to 0. Then the statement is true if a equals 0 is false. And this is called the negation of the statement a equals 0. So let's take another example. If we have the proposition 1 equals 1, well, that is true. Let's negate it. 1 is not equal to 1 would then be false. The truth table for the not operator is fairly straightforward. In terms of symbols we use for not, you might see this presented in different ways, but typically it's going to be the symbol half a rectangle, and could be used for not, or we're going to use the over bar symbol. So if there's a bar over a propositional variable, we're going to consider that the negation of the propositional variable. So given the formal proposition p, the compound statement not p, okay, so p with the bar over it, is a formal proposition known as the negation of p, and it's read as not p. And as I said, the truth table for the not operator is very straightforward. In this case, the not operator is only acting on one propositional variable. So in terms of the number of combinations we have, it's only going to be 2. So p, if that's the propositional variable we're considering, it can either take on the value of true or the value of false. If p is true, not p will then be false. If p is false, not p will then be true. Okay, so the truth table for negation just considers these two lines. Okay, in summary, we've looked at logic, and logic is of critical importance in mathematics, and it's really giving us the rules of the game. So how can we actually deduce various facts from given facts? And we've seen that dating back to Greek times, this idea of logic was playing a prominent role. We've had to look at the idea of a mathematical statement, and specifically we've looked at propositions, statements or mathematical sentences in which we can be clear about assigning a truth value to them. Okay, so there's no ambiguity here with these propositions. The propositions are either true or false. We've seen how using logical connectives or logical operators we can combine base propositions together to form compound statements that are themselves formal propositions. And we've had a look at how we can represent the actions of these logical operators through the use of truth tables. Okay, so let's take some examples.